Testing. Dominic, can you hear me?
Yeah, I can hear you, Professor.
I hear you.
All right, awesome. So I'm a little bit confused. I did write some notes, but I don't know if it was for my other Physics 37 class. So we had gotten through center of mass, and I did the thing for the cylinder. And I think I reviewed some triple integration real quick. But did we actually do the center of mass for the cone? Did I
No, I
calculate
don't
that?
have any cones in my notes.
But we did do everything else I just said, right?
Yes.
Okay. I mean, it's here. I could probably do it just to, sure, why not? Sure, why not? Since I had it in my notes to maybe do for you guys. So let's do that, and then we're gonna go on to center of mass, to conservation of momentum, and then to collisions. By the way, I was just looking at, I don't know how old this is. The Elon Musk and NASA, I guess they combined together. They're doing this, you know about this DART, this something asteroid reconfiguration test. I don't know what the D stands for. Um, it's where we send up this rocket and we're going to slam it into an asteroid and try to change the trajectory of an asteroid. Does anyone know about that?
Nah, that's the first I've heard of it.
Didn't that happen like a month or two ago?
It might have been. That's what I was going to ask. I'm not sure when that happened. I wasn't aware of it. But yeah, I was checking that out. And so have we already slammed it? No, it takes 3 months. We haven't gotten to it yet, right? Do you know?
I
Thought they
think we
said
did
so.
it, but I'm not 100% certain.
Oh, really? Wow. I didn't know that they had gotten to the thing. Yeah, I didn't really know much about that. It's kind of interesting because that's it's an inelastic collision is how that's going to work. And actually both, because I think they say that once it's going to be going so fast that it's 15,000 miles an hour. And I think, from what the guy said, that's the amount of time it takes if you blink your eye to go from New York to LA in like a few milliseconds. So
There's an article here on npr.org saying that they successfully did it as of September.
oh wow. 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 It was only going to change for about 3 millimeters or so, but uh, that's really incredible. So I was looking at the liftoff, but I guess they've actually done the thing too. So that's really fascinating. I wonder if they have any videos where they show us slamming in. I guess we could find them. But well, I thought I'd mention that because for some reason it came up on my feed in YouTube today. I don't know why I didn't see it earlier and know about it. So much going on in the world, it's hard to keep up. But yeah. Okay, well, you could probably find that stuff on YouTube. Then. Can you post that article on the chat room? We can all have access to it. Who said that? Was that Dominic? Who was that? Who had found that on NPR? Hello? Because I was looking at the internet. I didn't see who was talking when you said that. Oh, maybe it was. That was Dominic. Thanks for that. Cool. All right. Well, we'll get to that and let's see how that works in terms of momentum conservation. Yeah. So yesterday's problem was pretty straightforward in terms as center of mass problems go. But let's find one that's not so straightforward. Very doable and interesting.
Just to pick your brain a little bit as far as the dart test, you think it would
Yeah,
matter more the speed of the rocket they're throwing at the asteroid or the mass of it as
great
far as
question.
redirecting it?
It's a great question. And um, my answer, I guess, the way I would answer that question is that neither one of those are the most important thing. The most important thing is the product of the two, and that's what momentum is. That's what we'll see today. So hold that question to about the second half of class, and then we'll discuss it more in depth. But that's my short answer. Neither one is the most important, but the product of the two is the most important. And that's essentially what momentum is. Momentum is mass times velocity. So yeah, we'll talk about that a little bit more uh, in a second. A great question though, because that is the key question. You know. Um, all right, so we got a cone. We'll set this up. I like the axis the way I draw it, where it's a three-dimensional picture, but you're just showing two axes. Okay. Um, so here's our cone. I'll do a three-dimensional shot of this thing. So we got something going on, kind of like this. Take it out a little farther. I can actually. Okay. Yeah, I don't like that. Let me do it again. Just a little bit. A little sharper. Sharper like this. Oh, I see. Oh, it should come in like this. Yeah, that's a little better. No vantage point. All right, so we have that view, and then we probably need a side view, but just from the side view, I can just draw a right triangle. So we're gonna have the cone angle is really that whole thing. I believe that's how the cone angle is defined. And I'm just gonna do half of that, and I'll just call it what I want. So I'm gonna come out here and I'm gonna take a differential element, and the differential element will be, it's again, we're doing disks, but it's kind of like no matter how thin I make the disk, the radii, the area, this cross-section area of the faces of the disk are not quite the same. That's one thing. All right. And then it's over here. Not quite the same. So that's my differential element, dn. So I guess the question here would be find the center of mass of a cone of length L or height L and mass M. Find center of mass of cone of length L, mass M, and cone angle theta. Now I probably should look up cone angle because I can't remember whether it's half the thing or the whole angle. Hey Siri, what is a cone angle?
Here's what I found from reference.com. A cone has one edge at the intersection of the circular plane surface with the
Hey Siri, define cone angle.
Okay, I found this on the web, the define cone angle. Check it out.
Hey Siri,
Uh-huh.
what is a cone angle?
Here's an answer from reference.com. A cone has one edge at the intersection of the circular plate surface with the curved surface originating from the vertex.
So it looks like the cone angle is the whole thing. Yeah, it looks like the cone angle is that whole thing. So I'm going to make the cone angle 2 theta so that I can just deal with theta. Cone angle of 2 theta. So this angle here is the cone angle. Well, we could do this 2 theta, which equals I don't know, beta. So the cone angle is beta, and it's that whole thing, the whole thing there. So since I've set my cone up so that it's the bisector of the cone is along the y-axis, then beta, the cone angle, from a right angle equals half of that. Yeah. And I'm going to set this up, so I'm going to use cylindrical coordinates. So in cylindrical coordinates, I have a this is the z-axis. So z points along this direction. So cylindrical coordinates are going to be well, I guess I have to set up so that I guess the azimuthal angle will be theta. R, this is R right here. R is going to be pointing along, I guess, the z-axis. So the way I have it set up, yeah. So I guess that would be, so my R is in the XY plane. That's a little bit confusing. Z, so X, Y. I have a point along the positive Z. Well, how did I do here? This, what I say? It doesn't matter. I have to get. I'll go ahead and give the radius of the thing too. The radius is, so length L, mass M, cone angle beta, and radius R naught. And if my y-axis is centered here, I'll take this on out. Goes like that. Then my radius is this thing. Radius is the total bottom half. So the radius points, well, it's azimuthal. So rectangular coordinates are actually R phi And well, you're going to say Z, but Z usually is along the y-axis, along the z-axis. Is usually when you have something set up so that the height points along the z-axis. I guess I could do that. Maybe I should. But then I've got it kind of switched backwards too, don't I? As opposed to being sitting. I don't know why I did like that. Maybe because I wanted to stay consistent with what I had done over there. It's got it set up a little bit off because it's the length is moving along the y-axis. But I guess I could still integrate along the y-axis. So in this case, yeah, I just make it y. I could do that. So then y, where y is along the y-axis, and this distance right here, you know, like I guess this projected down is actually that total distance is L, just like it was with the other thing. So my R points basically, it's not necessarily along the z-axis, but it's R is rotating about the y-axis in the xz plane, and phi is the angle opening up. I guess you could say from the positive, yeah, because we can't see x. X is actually coming out of the board, so or would be kind of along like this direction. So the phi would be like this. This R, it's a vector that points out toward the edge of the circle. Actually, let me do a side view. Maybe a side view might be a little bit better to see. From a side view, the cone is going to look like this. So again, this is y, and that's z. So the cone is doing this. Should kick in pretty soon. So I'm doing it more. One of those days. Yeah, so the side view. So our R, our differential element is going to be this guy. Differential element is going to be like this. That's dn. And but the variable, actually, I think I told you, well, either R or I'm going to use rho because I could use R, but R sometimes is reserved for spherical coordinates, and rho is sometimes used for cylindrical. But it's the distance, the perpendicular distance from the axis, the y-axis, to the function, to the cone. And so at the back, that's actually equal to the radius, but that varies as you go from 0 out to L, right? So that's a variable now, rho is. So this is my vector rho. And here I showed it on the cone. I didn't want to show it there because I don't want to be confusing, but I could. It could be, you know, it's when it's on the cone, it's at that position. But in general, it's just it's a coordinate. So, and so what I was trying to show is that the phi is the angle that rho makes relative to the positive x-axis. But the positive x-axis is coming out of the board. So when rho is at 0 degrees, it's pointing out toward you. And what it does is it flips, if this is the y-axis, it opens up around the y-axis in 360 degrees. So you can see why it's called cylindrical coordinates, because, and then y, of course, is the position y where the rho is. So I guess now that I defined it, I can go ahead and I'm just going to go ahead and put it right back on the face, because I put it on the face here and I want the pictures to be consistent. So if I had done that, then rho would be pointing like here, right along the edge, up like that. So it's going to be the radius of the cone at every point. Maybe I should have done a different color, huh? Because you can't hardly see the red. Sure, let me make it black over here then. In this picture, I can make it black. Yeah. And so over here, I'm gonna call it rho, opposed to R. And it's a coordinate. So you can see how it can give you the shape of a cylinder, because it opens up in a circle about the y-axis, and it points out to, you know, however far you need to go out, and then it slides up and down. So it certainly could map out the shape of a cylinder, you know, if you had a certain length L, right? It's just gonna, it would be able to hit every point very easily on that cylinder. So those are cylindrical coordinates, rho, phi. And the phi, again, you know, like a lot of times you see it shown vertically, so you can show how the phi opens up. It's kind of hard for me to show it here, but if I were to shift the axis so that the y-axis were up, and I guess I'd have to change the orientation of the thing, because a lot of times you have the problem set up so that the y-axis, the bottom of the cone is back here at the origin, like it's flipped around the other way. I don't know why I did it this way, but it doesn't matter. It's going to still give you the same answer, but it's a little bit different from the way you might see this done or set up. And they usually make it along the z-axis so that the height of the thing will be along the z-axis. In my case, it's going to be along the y-axis. Doesn't really matter, but that's the setup. And the unit vectors are the same things as well, the unit vector for this would be J, but the unit vectors would be just like a rho hat, a phi hat, and a K. I know, usually if it's Z, it's K, but if it's Y, it's J. It's pointing in those directions. Oh, now, we're using mass density. Mass density is defined as mass per unit volume, right? But you don't necessarily have the volume of a cone memorized. And so that's why I reviewed the three-dimensional, why I reviewed triple integration, because with triple integration, you could easily use these coordinates to get the volume of a sphere, of the cone, so that you could actually define what the mass density is. Because unless we have that, we can only do the center of mass in terms of mass density. I think I showed you yesterday that it looks a bit more confusing. And we want to be able to compare it to the center of mass of the cone, which we know is 1/2. So we did that in terms of mass. So I'm going to go ahead and do a triple integral to figure out what the mass density of a cone is using cylindrical coordinates, so that we can use that when we find the center of mass. And you have to know what dV is, and you get this in calculus 3. dV is in the various forms, the various coordinate system, but I think I wrote it down. So in cylindrical coordinates, maybe I didn't do it here, maybe class. But dV is going to be equal to well, dy, of course, and then rho, d rho, because the rho can go from 0 to to wherever. Actually, the maximum value is going to be R naught. And the d phi is just d phi. So this, so rho, d rho, and then d phi. So this corresponds like I could do it for a cylinder, or maybe I did, I don't know, but for a cylinder, dV is equal to just dy dx, dx dy dz. And I think I did do that the other day. Sorry. Well, it's well, yeah. I mean, in rectangular coordinates, it's just equal to dx dy dz. And so this corresponds to that. And there's a whole way, to translate from Cartesian to cylindrical to spherical, or Cartesian to spherical. And you would have to go through that process to know where the rho comes from. It's not just a straight, you can't just write it down. And that's a little bit, that's beyond what I want to do here. So just knowing these though, and also you don't have to derive these every time. You can look them up in a book or whatever. In fact, they might actually have them in the appendix of your calculus book. But let's use it here to figure out what the volume of the cylinder is. So we just integrate, right? For the cylinder, for the cone. So for this cone, dy goes from 0 to L. Rho will go from 0 to R naught. And phi goes 360 degrees, 0 to 2 pi. And it just becomes a straightforward, straightforward, I don't know, maybe we need to take a look at this. So I'm doing volume here. So basically, I want to do every single, it's not so much L, this is a different problem than this guy. So first, let's say calculate the volume of the cone, just so we can get it. Find the volume of a cone, so that I can figure out the mass density, what the mass density looks like. And in that case, it's not so much an element we need, we just need to find every point on the cone and map that out within the interior of the cone between its boundaries. And so for that, it might be more useful to think about we can just look at a right triangle, like just half of the cone. right? To show what the coordinates are representing. So if I took half of the cone, so half of my cone angle is going to be this theta, right? Right here. And my R, my vector here is just, it points, so this is the y-axis here. So this is along the y-axis. So this vector here points from y to the, to the edge. There you go. So that's rho. So rho has got to get all the points in the space on both sides. So that's how I'm taking the, y is going to go from 0 to L to get everything there. The rho takes every point as you do that between the y and the edge of the cone right there. So it goes, in fact, it doesn't really go to R naught. That's not true. It goes to the function, whatever that function is. So that we have to write that in terms of a function of R. That's the problem with this, I think, right? Yeah. It's not actually R naught. It's some value of whatever R is at that point. So I'm going to call that small r. Because it's only R naught whenever y equals L. But when y doesn't equal L, it's not R naught, but it's just some function. I'll call it just R. Guess we could say that. So that, yeah, I'll go ahead and put the L out there too. So this goes to, this distance is L right here, y equals L. Yeah, and so I guess I have to write R in terms of, well, let's just go. Yeah. So we'll do these in pieces. The phi, there's nothing funky about that. It just goes around to 2 pi. So I can do that integral and take it out and put it over here at the front as a constant. So let me go ahead and do that. Again, with triple integration or double integration, there's nothing fancy about it. You just do integrals of each piecemeal, and then they just multiply one to the other. So this integrates to dv integrates to, so it's going to be 0 to L dy. Well, let's do it like this. And then rho d rho 0 to R, where R is the radius of the element at each point, or the length of the thing, if you make that a thin disk at each point. And then this just goes to phi, integrates to phi from 0 to 2 pi. So then this becomes dv is equal to, bring that out front, 2 pi times integral from 0 to L of dy, and then integral 0 to R of rho d rho. All right. Yeah. So now, yeah. So now we can get the other one. We'll get the second one. R just goes from 0 to whatever that R is. Can't be R naught, just R now. And so that's a simple integral as well. There is a little bit of trick here. We'll show you in a minute. So dv is equal to 2 pi, and then we have 0 to L dy. That integrates to rho squared over 2 from 0 to R, So now that becomes dv is equal to 2 pi times integral 0 to L dy times basically just stick an r in there. So r squared over 2. Now here's the issue. It gets a little tricky right here because that's just you can't just stick an r naught in that because the r is related to, it's not a constant, it varies, but it varies relative to y because they are related, right? As r changes, y changes. And you just can see it here. As this thing moves down, it gets longer, but there's a one-to-one correspondence between the particular value r, the radius of the disk at that point, and the position y. So this thing r is dependent upon y, so I have to figure out what that dependence is, then stick it in this integral and integrate with respect to y. So what happens is I can go ahead and cancel out these 2's. They cancel. So that 2 cancels that 2 right there. And so now the integral that I need to work out, well, I just do that. And then, so what is that relationship? Well, you use any kind of relationship that you can, any kind of concept you can to get the relationship. And the easiest relationship that I can see is tangent. Because for this little right triangle right here, like, so I have a value of y right here, whatever that is, that's where I am. And on this case, it would come up to here, like when we get back to this problem, y is the distance from the origin to the front of my differential mass. But if I'm just calculating the volume, there's not really a differential mass. It's just basically I'm trying to find every point in space and add it all up. So this is a very thin thing right here, and it just has position y. It's not like an element, a physical element. And so, but still, for every value of whatever r is at this point, it corresponds to a y. And so the relationship between that value r and the value y can be defined by this right triangle right here. That's a right triangle. So, and obviously it's tangent. It's tangent because tangent of theta is equal to r over y. And that's kind of the trick with a lot of integration. There's no rules. It's just whatever you can find to make those relationships. So tangent theta, which is actually constant, right? And remember, or did I say, and remember that's theta, that's not phi, that's not the angle coordinate opening up. That's just the angle or half the angle of half the cone angle. So tangent of theta is equal to r variable over y variable. So theta is a constant, but the ratio of r to y, r changes and y changes, but the ratio of r to y, which is tangent theta, is a constant. So that allows me to write r in terms of y. Why didn't it come out over there though? Why did I need to do that there? Oh, but that's, yeah, for the center of mass, I'll have to do that. But for the volume, I just need the whole thing. So maybe I was wrong about that. For the volume, I just need to, I do want the whole thing. So I guess I don't have to do that. Think about that for a minute. The r squared is out. You know what? dx really not writing here. Sorry, folks. Should have looked over this before. Where am I getting the x squared from? Oh, duh. Yeah, maybe I do need to use it. So let's just keep going. So yeah, sorry. Shoot, explicit. I don't know why. Oh, I don't need this. So dv. So I'm just trying to find tan. So I can do this. So yeah. So tangent theta, it actually equals ry, but it also equals the larger right triangle. They're similar, right? Like if I go to this whole right triangle here, that's also the tangent theta is also uh, uh, r naught, which is the radius, over the whole length L. So all those are valid. Tangent theta is equal to r over y, but it's also equal to r naught, capital R naught over L. So I think there, what I did, sure. So, yeah, I see it now. So what I then did is use this equation here to solve for R. So if R then 8, R is equal to Y times R naught over L, then what I need is R squared. So R squared then is equal to Y squared, R naught squared over L squared. In equation 9, I can substitute into equation 6, and then I can integrate. So that's how you have to get the relationship between R and Y, because R is dependent upon Y, and so you're integrating. So that's how you do it. So that's cool. So then I substitute that in, and I'm going to have so dV is equal to, I've got the pi out there. I just substitute in so I'm making mistakes and leave out anything, and then do the algebra. 0 to L dy, but then R squared is going to be what I said. It's going to be Y squared R naught squared over L squared. Now, R naught squared over L squared is a constant. It comes out of the integration. So this becomes dV is equal to pi R naught squared over L squared, the integral from 0 to L of Y squared dy. Simple integral, just integrates to y to the 3 over 3. And so then we get V, actually, because you got to integrate that side as well. So then V equals should put an integral sign as soon as I have that. So then V is equal to pi R naught squared over L squared times Y cubed over 3 from 0 to L. And so the volume of a cone equals pi R naught squared I mean, you could look up the volume of a cone in a book, but I just, it's just to show you some triple integration. Thought it's cool to do it, to work it out. So you could have looked this up, but whatever. So then you have L squared. So L squared then times L cubed over 3. So one of the L cubes cancels, right? Or 2. So that guy goes, and that guy I have 1 left. And my final answer, yeah, that's right. And you can look this up and verify it, that the volume of a cone of length L and radius R naught is equal to pi. Well, actually, I take the 1/3 out. So 1/3 pi R naught squared times L. That definitely has units of volume. R squared times L is cubic meters as a unit. So at least the units are right, but that is what I have in my notes. And we can compare that. We know it should be less than the volume of a cylinder, and the volume of a cylinder is just pi R squared times L, right? Pi R squared times L is the volume of a cylinder, or H, or whatever the length is. So basically, by taking a cone, you're getting 1/3 of the volume. Isn't that interesting? 1/3 of the volume of so a cone. If you cut a cone out of a cylinder, then you're cutting away 2/3 of the volume. That's interesting, and you get 1/3 of the volume left. Interesting. Okay. So let's see what the center of mass. So basically now I know explicitly in terms of given quantities, I know what my mass density is, because now I just multiply my mass times that, and I'm going to need that quantity whenever I do the center of mass. And we'll take that with us. I'm going to erase all this stuff. But the final thing is I take 14 and I plug it back into this equation 1. And so that my mass density is equal to 1/3 pi times the mass times R naught squared times L. So that's going to be useful information that I use. Oh, wait a minute, no, I'm dividing by that. So my bad. I'm dividing by, so it's not true. It's actually going to be my mass density is going to be equal to 3 times m divided by pi R naught squared over L. Yeah, that's my mass density. Okay. All right. So all I need from this basically is this thing, or really these two. I guess we could have both of those, but really 15 is what I need. So I'm going to now erase equations 1 through 13, and then go back to the problem that I really need to do, which is this guy. So can I go, or is there any questions or anything?
Looks good to me.
Is that Dan? Yeah, is that Dominic?
Yeah.
So what math are you in, Dominic? Have you had?
Calc 2.
Okay. All right. So what's in Calc 2? Have you done? You started doing? Do you have double double integrals, triple integrals in Calc 2 or no? What's Calc 2? What are you doing in there?
Tell you the truth, I'd have to look at my notebook. Don't know off the top of my
Okay.
head.
All right. Okay, so let's go back to this. Now, let me keep that set up. And we had our equations for center of mass. And I'll do the one where I'm clearly going to be integrating along the y-axis. So I'll write that down again and we can see how we can use that to figure out this guy. And again, our intuition tells us that the way I've set it up, I guess that's why I've set it up, is because it should be larger than L/2, which is what it was for the uniform cylinder. And I'm cutting the cone out of the cylinder and shifting it so that most of the mass is, at the, in a position where y increases. So we'll see if our answer is consistent with that. So starting with yeah, how did I have it set up? I set up so that the equations I gave you yesterday were just keep this number, so 16. So we want to know RCM, or actually, well, really, we know that the ZCM and the XCM should be 0 because I have it centered along the bisector. So those two are 0 just, from observation. So really what I just need to calculate is the YCM. And that's going to be rho over m times the integral of y dv, but then dv is equal to so how do we have to express that? In this case, the cross-section area is not constant as we move out. And I want to try to, so really it's a double integral at least, but I want to try to pick my differential mass so that I've kind of incorporated that. And I guess, again, I can go back to that right triangle that I had, and that still does it, right? It does it. So I guess this is a y dv, right? So I got to figure out so the y is just the position up to where my element is, but what is that differential volume? How do I express that? And just to remind you, I'll come back here. We'll do it again. So at any point along this thing, so if I have my guy again, my right triangle, so this is R, it's at position Y. And this distance here is R. So at any point, the area or the volume of any little cone I could map out, any subcone that's within the larger cone, where this is radius r naught, and this is length L. The volume of that small cone, you could say, is equal to pi, the area of the bottom of the cone times the height of the cone at that point. So for this small cone, that area is pi r squared, right? This cone right here. And that height, or the length of the cone, is y. So for a small volume that I guess you could call it a differential volume, right, in a sense. But anyway, I don't know. But for that small volume of that, that's going to be pi r. It's going to be y times pi r squared. But I'm along yeah. But really, I don't have the whole y. I just have a differential y. So that if I were just at some space like, let's do this again. If I just had something like this, then this portion here, the height is just dy. And the area of each of these, like, I know that r is varying, but each segment that I make out would have like an area r. So if I added up all of those pi r squareds and multiplied by dy, it would give me the volume of this whole thing right here, of that whole thing. So then what I could say is that, and I guess I have an RDR too, don't I? It's really a double integral. It's a dy, and I have to take the derivative of that thing, which is 2r dr. But what I'm going to do is in terms of a single variable. So what I could do is write r in terms of y, and then I don't have to do the double integral. So that's really what we can do based on how I'm choosing my relationship there. And again, that relationship that's theta. So technically speaking, this dv with respect to my elemental unit that I'm choosing to integrate is going to be equal to, and I'll put it over here again for you, that r, so tangent theta, well, I guess I could just do it here. And I can say that because, again, both r and y are changing. So my dv, really both y and r are changing here if I want to make that a differential volume. But I don't want to have to do a double integral, so I'm going to change it, find how r changes in terms of y. And in doing so, I can use my geometry that tangent theta is equal to r over y, which is equal to capital R naught over L. And so r squared, again, as we've seen, I can do it in terms of either one. It doesn't really matter. But I'll use this one since I'm going to have to do that anyway in the end. Then r 18, or either one, meaning I can use ry is equal to tangent theta or ry is equal to r naught over L. But I'm going to do this one because that's what I have. I could do either one, but I'm going to do this one just to make it look like we did yesterday. So R is equal to Y, R naught over L. I think that's what I did. Well, you know what? I'm gonna stick with my notes just so I don't get screwed up. For some reason, I did with tangent theta, and then when I finished, I substituted. It doesn't matter because in the end, tangent theta is a constant anyway. But I just don't want to get too screwed up. So sure, R then is equal to Y tangent theta. So now I'm going to take that and substitute it into here, and so then my V, my small volume is going to be equal to Y. So I have a Y here times pi. Well, actually I have to square it, don't I? We have to square it. Yeah. So R squared is equal to Y squared times tangent squared theta. And so then R, so then if I take 20 and substitute it into 17, then I have 21, which is V is equal to Y times pi times Y squared times tangent squared theta, which is the same as Y cubed times pi times tangent squared theta. And somewhere along, I needed to have the dy. Where does that come into play? It's because right. No, it was dv. So dv, this is v. So dv is so how do I get the dv in there? I'm sorry, folks. I should have reviewed this before I looked at it. Yeah, my bad. That should have been a dx. Dx is there, yeah. And then x squared. Dx pi r squared. Yeah. Somehow I got it tripped up here. Let's go back to here. Sorry. So I'm going to write R in terms of Y, but I've got to, like, what I really want is a differential volume. And the differential volume, I guess I could put the dy in here, because if this is the volume, I forgot to do that, like of like a regular triangle like this, but I want a differential volume. So it's going to be, yeah, that's what I said. The volume of that thing is just dy times pi r squared of each one of those. So adding all those up. So if v is equal to y pi r squared, then I guess I make this a 17b. Then a dv, which is really what I want, is equal to a dy times pi r squared. Now, technically speaking, I should also, I guess, take the derivative of that, but it's with what I'm going to do, I'm going to substitute in this thing into there before doing that. Yeah. Yeah. So yeah, now substituting, yeah, I forgot to make this just a dy, so we're good. So now 21 or 20 is going to be equal to r squared, y squared. Well, r squared is equal to y squared tangent squared theta, and now putting 20 into 17b. So that's going to give me 21, and that's going to be that dv is equal to dy times pi times r squared, but r squared is y squared tangent squared theta. Okay. So now we're good. We're good. So now I'm going to take 21 and put it back into my original formula for the center of mass. And that's this guy right here. So taking 21 and putting it into 16, that's going to give me 22, which is y center of mass is equal to rho over m, the total mass, times the integral of, now there's a y that's still there. That y is there, y. And then my dv is all of that. It's going to be dy pi y squared tangent squared theta. Now, only y, pi is constant and tangent squared theta is constant. So they come out of the integration. So this would be 23. So then YCM is equal to, so the tangent squared and the pi come out. So I've got rho already out there. I've got total mass already out there, and then times pi tangent squared theta. All of that stuff is, constants. And then here I just have y cubed dy, and that goes from 0 to L. Yeah. So that's a simple integral. It integrates to y to the 4th over 4. YCM then is equal to rho pi tangent squared theta over m. And that's a y to the 4th from 0 to L. And so we get YCM equals rho pi tangent squared theta over the total mass of, and then times basically L to the 4th over 1. And actually, that's the answer. That's one answer in terms of mass density. But like I said, that's kind of confusing because it doesn't even look like a length with all that stuff in there. So we want to get it back in terms of mass, not mass density. And so we need to make substitutions also for tangent theta. So remember, tangent theta is also equal to R naught over L, and rho is equal to 3m over pi R naught squared times L. So if we substitute all that stuff in, let's see what comes out. So YCM is equal to, so put in the rho, and that's going to be 3m over pi R naught squared times L, then times pi over m, then times tangent squared theta, which is R naught squared over L squared, then times L to the 4th over 1. Let's see what comes out. So there's a pi that cancels here. There's an R naught squared that cancels there. I have an M that cancels here. Oh, and you know what? I forgot the 1/4. The integral is y to the 4 over 4. There's a 4 there, and that's a 4, and that's a 4. Okay. So what else? I have an L here and an L there. That's L cubed. So they cancel, and I have just one L left over here. So that my total thing, so YCM, is equal to I have a 3, and I have over 4, and then L. So it's going to be 3/4 L. How about that? I find that quite interesting and symmetric. That when we carve out a cone from that cylinder, the cone is, the volume of the cone is 1/3 of the total volume. Actually, the mass density should be constant, so that should have been the same as what we had. So is that true? So if that's the case, then I wouldn't have had to do it. Is that the same? No, it's not. The mass, why does the mass density change? Because of the volume change. But, so what I had, well, the point is that the center of mass shifts. It shifts from 1/2 down to 3/4 of L. So that's interesting. It does get larger, or I guess a larger, farther down along our y-axis that we expect, because we expected that, right? 1/2 is less than 3/4, but it shifts basically between another, like a quarter, which I think is, that's not intuitive to me that it would necessarily be right at that particular point, but I guess it is. But it just occurred to me that, did I really have to calculate the mass density again? Because if it's uniform density, it should be the same. So, but why is, oh, right, because but it's the same radius though, as the cone, as the cylinder. So the mass density would be total mass over the total volume of the cone, or total volume of the cylinder, and the volume of the cylinder is pi r. Oh, I got it, because it's different. The mass, and it's not the same mass. That's right. That's why. It's not the same mass. It's not the same mass. That's where the 3 is coming from. Because I didn't have a number. I just had a symbol M. So obviously this mass is a different number than the other mass. Interesting. So that's it. Oh, that makes sense. So that volume was just M over pi r squared L. Yes, of course. So that means that the mass of this thing is 1/3 of the mass of the other one. And you can see it there. That's where the 3M is coming from. Okay, got it. Wow, yeah. So little things like that you just want to think about. And it just kind of, if you think about them, put a little mental thought, energy on thinking about them, it kind of makes everything, it'll make more sense. So that obviously if the density, because I said that the density is uniform, right? So my first thought was, well, maybe it doesn't change, but then, well, it doesn't. That whatever that value is of the density, it'll be the same as the other value of the density if I given numbers, but I didn't give numbers. So I just had it in terms of a symbol, but it's important to realize that the masses are not the same, but I use the same symbol. So really, I'm writing this density in terms of the original mass of the cylinder. And that's why this is 3m. So in other words, you would have to have 3 cones, which is what we're saying. It's a third of the volume. So you'd have to have 3 of these cones to have the same mass as the original cylinder. So that's what this is saying, 3 times m. Okay. Okay, awesome. Awesome. Well, you know, that's center of mass. Any questions? Find that a bit interesting. Yeah.
So
Yeah.
if we started off with the mass being 1/3 m, equation 15 would just end up being m over
Pi r squared L, yeah, which it should be, because we said that the density doesn't change, you know, density is constant. So that density would have been the same. That would have been the same relationship as we had in the beginning. You know, like when we did the cylinder, the density was just the mass over the volume, but the volume is just pi r squared L for a cylinder. And so then the density is just m over pi r squared L. That's what we got before. So it kind of threw me off a little bit that when I did this, I didn't get the same thing. I got 3 times that. But then I realized, well, this is the mass. I should put like something that the mass of the cone is equal to 1/3 of the mass of the, but I actually didn't know that. So now this is one way to prove it. The mass of the cone is actually, well, I guess cone and cylinder, so not a mass of the cone is 1/3 the mass of the cylinder. All right, something like that. So this actually proves, because that could be a question, right? Like if you just carve a cone out, you know, what's the mass of one relative to the other? This is, I guess this is, never thought about that, but this is one way to actually show that, I think. Yeah.
all about perspective then?
Say again.
All about perspective. One thing you consider a mistake turns into more opportunities.
Yeah, I guess so, right? That's what they say. You always learn from your mistakes. Learn more from mistakes than you do from successes. This is probably an example of that. So then you would compare the densities, you know, of the cone versus the cylinder, and that would show you that's it, because you know that they have to be the same. So then everything would fall out, and you end up with this relationship that the mass of the cone is equal to 1/3 the mass of the cylinder. Cool. I'm sure we passed the break time. Oh, we just passed it, only 5 minutes. All right, well, we're done with that. We're going to move on to take a little break, and we'll come back and we'll talk about conservation of momentum, and then move on to collisions. All right. So what I was saying is that we're going to start conservation of momentum, and introduce that, and then use that to figure out use it for collision problems. But it's always important. And I'm sorry, I'm really tired today for some reason. I'm kind of crashing right now. So believe me, I'm not. If my speech slurs, it's not because I'm drunk or Anything. I'm just really, really tired. So conservation theorems, it's important to know when to use them. And we want to reiterate the criteria for usage for these conservation theorems so that we know when to use them or not using them incorrectly. That's valid for any concept actually, but certainly for the conservation theorem. So does anyone remember what the criteria of use is for using when it is valid to use the conservation of energy theory? When is mechanical energy conserved? Anyone? Armand, do you remember?
Sir, I'm trying to just understand the question. Can you just reinstate it one more time?
Sure. What is the criteria such that mechanical energy is conserved?
The criteria that states why it is conserved?
No. The criteria such that you know that it is conserved and therefore you can use conservation of energy to apply to that system.
It's a closed system? Is that one?
No, is the volume bad or something?
No, I just don't think I'm understanding the words. The criteria that we know that exactly that energy is going to be conserved. Don't we always know that it is going to be conserved?
Could you is that a question? Did you just ask me a question?
Yeah, it's not my question because I'm not really understanding the wording here.
Okay, could you ask me the question again?
What do you mean by criteria? If you mean that energy is always conserved, is it conserved in the amount like, oh no, the energy does not get destroyed or reproduce? It always just, it's because of the law of conservation of energy. We always know that it's conserved, or is it by some other like specific method saying, oh, is the energy in the car conserved that's crashing into this one, or is it being repurposed through like sound or deformation or other things? I think I understand what you meant by that.
Okay, fair question. So, do you remember when we talked about motion? And I split motion into various categories: general motion, free fall, parabolic. There was always a criteria that told you when an object was in free fall motion and when you could use the equations associated with that concept. Do you remember that when I used criteria in that context?
Yeah, I recall.
So do you remember, for example, the criteria that lets you know that the motion is free fall?
It's in the back of my brain. I'm trying to remember it.
Okay, anyone want to help me out?
Is it only if it's if the object in the system only being acted on by gravity?
Awesome. Yes, that's right. So that the acceleration will definitely be acceleration due to gravity. So that is what I mean by criteria, that mechanical energy isn't always conserved for various systems. You have to look at it and analyze it, and there is a certain criteria such that you know the mechanical energy will be conserved, and therefore you can use the conservation of energy to solve the problem. Because you see, unlike Newton's laws are much more straightforward and kind of brute force. So it's very hard to misuse them, right? If there's forces on objects and you know what they are, it's just straightforward. But when you start to get to more elegant or more powerful mathematical or physics concepts, there's a subtlety that arises. So with conservation of energy, for example, you can use it on whatever point for problem you want. And there's nothing in the problem that will tell you you're wrong. Because if you can't use it from the beginning, because the criteria of usage is violated, there's nothing in the mechanics of working through the problem that's going to tell you that. So that's why I've spent a lot of time stressing the criteria of concepts in general. And again, with free fall motion, it's a little bit harder to misuse it because even if you just, because it's obvious when something is in free fall, right? When you're, maybe not reading a problem, but if you understand what the problem is illustrating, like a ball falling through the air, then it's obvious. And certainly if you see a ball falling through the air, it's obvious. But you can take an object and put it on an ideally frictionless surface like ice or something, and this where the coefficient of friction is negligible, and it slides down the block plane. But then put it on another plane that might be smooth, but it's not technically frictionless, and it slides down the plane. So in one case, mechanical energy will be conserved. In the other case, it won't be. And it's not obvious because the motion of the object is the same, right? So
Yeah.
that's what I mean. Like, so you have to be a bit more careful with any conservation theorem, energy, linear momentum, angular momentum. So I really emphasize that that's why I'm starting this lecture with reviewing the criteria for conservation of energy, because now that we're going to learn a new conservation theorem, I want you to, not just focus on the theorem, but focus on the criteria of usage, because it's even more important now than it was, anytime you apply to a conservation theorem, in my opinion, than a lot of the other concepts. So the question is, we specified that there was only certain times when you could use conservation of energy, and that the criteria of usage had to be satisfied. I'm asking you, what is that criteria?
If only the interior forces are doing work and there's no energy added in from an exterior force.
State it one more time, please.
If only the interior forces are doing work and there's no exterior force adding in energy or work, not to be, sorry, into the mechanical energy, I believe. I just didn't find the quite word, sorry.
What was the last thing you said? You just what?
And I couldn't find the right wording for it. If only the inside forces are doing work and nothing's being added from the outside, that's it.
Well, that's a pretty, I've never heard, the statement like that before, certainly regard this, but pretty interesting statement, but that is not the case. But when you say internal forces, like if only internal forces are acting on an object is not going to move. And it's otherwise you would have a perpetual motion, you'd be able to make a perpetual motion machine or something like that, right? Because Newton's law says that acceleration only comes when you have external forces to a system. But you're kind of, yeah, like that's what I would say, that it's not internal forces. It's a different, another kind of force. But internal forces, if they're not doing work, that means, well, yeah, like internal forces, it's kind of like me trying to translate myself by twitching muscles. The only way that's going to work is if I'm like, maybe if I were an ice skater and I'm on ice, I could dig in. I don't know, like you would need friction or something in order for that to happen. So no, that's not quite the answer I'm looking for. And it's not what makes you be able to use conservation of energy. Yeah, so it's not external forces that can only do work. It's some other kind of force. What other kind of force am I talking about? Have we talked about? Anyone?
Are these the same criteria for conservative forces by any chance?
Well, it's related to conservative forces, but the criteria of a conservative force is not the criteria for when you use conservation of energy, if that's what you mean. There were these three criteria or definitions that define a conservative force, and the negative of the three that define a non-conservative force. But this question that I'm asking you, this criteria of usage is associated with conservative forces. What about it? Are you getting more? Anyone? No more tries. Malachi, David, Theodore.
Yeah, I'm not too sure. I'm thinking about it. I don't know who was speaking initially, but I would have said the same thing as him. So
Okay.
being completely transparent, I'm not gonna, lie. I would have said
No
the same
worries.
thing.
Appreciate that. Well, the wording is kind of right, but it's not internal forces. It's conservative forces, right? Mechanical energy is only conserved whenever, well, mechanical energy is conserved when only conservative forces are doing work on the system. That's definitely not the same thing as internal forces. They don't have to be internal, they can be external. Because gravity is an external force, but it's also conservative. So when it does work on an object, if it's the only force acting on the object, then mechanical energy will be conserved. Basically, I think I told you that a quick and dirty way to distinguish between conservative and non-conservative forces is that if a force is touching an object, it's going to be non-conservative. It's going to generate friction as the object moves or in the process of doing work on it, and it will convert mechanical energy into heat. Now, one possible exception to that is the normal, and that's to not be confused. Like a lot of people interpret that to say, well, what I said was if only conservative forces can do work on the system. So what a lot of people interpret that is to say, and I can't remember the wording of initially as well. I think it was Armand. But a lot of people say, well, the criteria for usage of conservation of energy is that only conservative forces act on the system. That's not true either, because normal force will act on the system in both of those scenarios I talked about, like sliding down a plane or whatever. But the normal force, it is a force of contact, but it's not the thing that's taking energy out of the system directly. The normal force is associated with the frictional force, and therefore it's the frictional force that's actually doing the negative work and converting heat, mechanical energy. The normal force is doing no work because it's always perpendicular to the motion.
So then, does that mean? So let's say if I roll a ball down a plane or like a hill, I should say.
Mm-hmm.
So then that would be a conservative force or non-conservative, because you're saying that if one object is touching another object, then it's a non-conservative force, right?
Yeah.
Yeah. So a ball rolling down the hill, would that be considered non-conservative because the ball is touching the hill?
Yeah. Well, what forces would be on that ball? Name all the forces on that ball in that case.
The normal force.
Sketch a little.
Yeah, it was
normal force.
normal force and like not gravity, wind resistance.
Well, let's assume there's no wind. That just complicates it. Let's assume
Okay.
it's in a vacuum.
I'm drawing it out right now.
Okay.
That's like that's it. Forgive me if
What'd you say?
I said that's it.
What forces?
The normal force and not centripetal, because it's not spinning in a circle, it's just going down the hill.
Yeah.
So that's it. Sorry, I'm a little tired.
It can't be the only force on the object. It's normal force. That's okay. Let's just knock it out real quick and let's see. So if we have something rolling down a hill, sure, we've got the normal force. That's the mass, right? Normal force is going to be acting in this direction. Yeah.
Yeah.
Surely, I mean, if that's the only force, then the object will go up, right? Otherwise, it's a violation of Newton's law. So
Oh, yeah. So gravity then. Yeah.
Yeah, obviously gravity. Yeah,
My
straight
bad.
down.
Yeah.
That's all right. All right. And if it's, assuming a pretty realistic case, if the coefficient of friction associated with the surface, as the thing moves down, what other force would we have on it as it slides down the plane?
Friction.
Friction, yeah. So clearly that energy is not going to be conserved, because as the thing moves down, friction converts the thing to heat. Okay, and so some of that, yeah, so it's not conserved. Now the normal force, because the object is moving down the plane, the normal force is not doing any work. Why is that? It's because, remember, work is equal to F dot dx, right? So the normal force is straight up. You got to work out that dot product. Like, so if you try to figure out the work done by the normal force, then you have to work out the dot product first. Dx is down the plane. And so n dx cosine theta, it's going to give you 0, right? Because dx is, the angle between them is 90 degrees. The cosine of 90 is 0. So a normal force does no work on the object, even though it's there. Even if it were a friction, it has nothing to do with friction. I mean, it's 90 degrees, so it doesn't do any work. Now, if there is friction, through the frictional force, it does work, right? Because friction is definitely doing work. It's doing negative work. If you do the same thing, the work done by friction is the integral of F, basically dx times cosine of 180, because dx down the plane, F up the plane, they're in opposite directions, kicks out a minus sign. And if we, and so we have minus the integral, and the friction force is defined as mu times n dx. So we figure out what n is, and then we go on and so forth. But the point is, it's going to be non-zero, generally speaking. In this case, it would be. So that doesn't mean the normal force is doing work, because that was part of the frictional force. The frictional force is doing negative work on the object. So in general, a quick and dirty way of determining whether energy is going to be conserved is because I can kind of do this without actually working out any numbers or anything. I can qualitatively assess just by in steps 1 through 4 what's happening with the system and whether or not there are any conservative forces, whether or not they will be doing work or not. So that will tell me whether or not I can use conservation of energy specifically. And even if I can't, then I can use work energy theorem. I think I derived that for you, so you can use work energy theorem in the modified work energy theorem in lieu of conservation of energy. But the point is, you need to know, right? So if energy is conserved, you can start here, delta E equals 0, right? E final equals E initial. If it's not conserved, you start here, delta E equals the work done by the non-conservative forces. So that ends up being E final minus E initial equals the work done by the non-conservative forces. Conservation of energy, modified work energy theorem. But the criteria is, if non-conservative forces are doing work on the system, then mechanical energy is not conserved, and you would have to use modified methods to figure out what the conservation, to apply to the problem if you want to use conservation theorem to solve the parameters and analyze the problem.
All right, yeah, I see that. Thank you.
So again, with all that, who went first? I think Armand, but anyone. Theodore, are you there? So Armand, go for it. Thank you were first. What is the criteria such that mechanical energy is conserved?
This, if the conservative force remains, I'm sorry, my brain just brain farted. If the conservative force remains the same, or conservative energy remains the same.
That's kind of answering the question with the question. I've told you that it's conserved. So I'm saying that if it is conserved, what is the criteria that it is conserved?
Energy remains the same on both ends.
No, that's not the criteria. That's actually what happens in the context, So I'm asking you, what is the criteria that energy is conserved, that the mechanical energy remains the same? The answer can't be that the mechanical energy remains the same. I mean, there's another reason why that's happening. I mean, I guess it is the answer, but it's a trivial answer. So that's not what I'm going to. So let me write it down. So you got to put it into, because I'm going to ask you this again. It's probably going to show up on other things. So You need to know this. And also, we're going to do the same thing for conservation of momentum. So you need to know that criteria as well. So the criteria that mechanical energy is conserved. Mechanical energy of a system mechanical energy of a system is conserved when only when only conservative forces do work on the system. That's it. So the change in the mechanical energy is zero through some time period. And this is a statement of conservation of energy. The modified work energy theorem must be used whenever energy is not conserved. Such that delta E, the change in the mechanical energy, will be equal to the non-conservative forces that are working in the system. Because that's when mechanical energy won't be conserved. Obviously, when the negative is just from there. Well, actually not necessarily, but whenever non-conservative forces act on the system. So that we will use in conjunction with what we're about to do now to do collision problems. You do collision problems with a combination of conservation of energy and conservation of momentum, depending on the situation. Well, you always use conservation of momentum. Momentum is always conserved. Energy is either or, it is or is not, depending on whether conservative or non-conservative forces act on the system. So that said, and anytime there's touching, then you know that energy isn't conserved, technically speaking. But there's a way, well, we'll get to that. So now that's conservation of energy. What about conservation of momentum? As I said, we start with Newton's second law. And this is linear momentum. There are different kinds, there are different kinds of momentum. Well, linear versus rotational or angular momentum. So we start with Newton's second law, that net force of a system equals the mass of the system times acceleration. Then we can remember the definition of acceleration. It's time dependent, right? So it's d dt of the velocity, with respect to time. Now, if we take 2 and substitute into 1, we have that the net external force, that's external, not internal. So I don't know how you get on the internal thing. Internal forces would be, you in space trying to move, trying to translate through space, trying to swim through space, right? You can't do that because it's a vacuum. So you can move all you want. And when you're doing that, it's internal forces, but it's not going to make you translate. It might make you rotate. In fact, it won't make you rotate because even that, you can't do any external torques either. So my bad. You'd have to press on something in order to make yourself rotate or pull against something that, like water molecules when you're swimming, it gives you drag and friction and actually a normal force that you can push against, Newton's third law. But if there's nothing there, you can move all you want and internal forces are going crazy, but your average position is not changing because of the motion. So if you're not moving at all, then you're still not gonna move, even though all your internal forces are doing all kinds of work on whatever. So it has to be an external force. And if I substitute that in, then I have that that equals the mass times the time rate of change of the velocity. Now, this is a nice result here because normally mass doesn't change. But we were just talking about the shuttle going, the DART program or any kind of space, rocket or whatever. With those things, and I thought it was really interesting because they had the external camera, and I guess Musk has finally perfected the booster thing coming back. So the booster separates, it falls back to Earth, and then it basically flies back and lands, out in the ocean on this thing, so they can use it over and over again. And that was cool to see, and to see it coming back down itself and the camera on, watching it come down. But my point is that with rockets, most of the mass of the rocket initially is fuel. So as the rocket goes up, the fuel is burning, so the mass is changing dramatically, and it can't be considered a constant. So if the mass is also time dependent, it can actually come inside this integral. So if we place it, or this differential operator, excuse me. So net external force is equal to the time derivative of mass, which is time dependent, times speed, which is both time dependent. Now, here I can define a specific quantity. Mass times velocity, that is a thing. Mass times velocity, we can define it as momentum, linear momentum. We give the symbol P to represent it, and it is defined as the mass of the object times the speed of the object. And they can be constant. It has nothing to do with whether the quantities are time dependent or not. Even for a constant, even if mass is constant, and speed for that matter too or not, this is still the momentum of the system. It's the mass of the system times the velocity of the system. Now, instantaneous momentum gives you gives you time dependent. If instantaneous momentum is determined by a time dependent velocity, but if it's an average velocity, it just gives you the average momentum. And if it's a constant velocity, that means the momentum of the system is not changing. Well, actually, that's not true. The implication is there, but there's it kind of gets toward the criteria, but I like to state the criteria in a different way. But point is that this is actually momentum. This is momentum right here. Momentum is defined as mass times velocity. Okay, linear momentum. Mass times the linear velocity. This is linear momentum. Okay. Now I'm going to take that and substitute back into equation 4 for just a second. And what I have then is that the net force on an object, external force, is equal to the time rate of change of the linear momentum of a system. And that is a result. That is a different way of stating the second law. It's just as valid as F equals ma, but it's clearly a different formula. So yeah, so F equals ma. It's one statement of Newton's second law. But actually, this statement is more closely to how Newton defined the second law when he first wrote it down. But the way you state that is that the net external force on the system is equal to the time rate of change of the linear momentum. Now, your book might define momentum from a different way. It might say something like, well, whatever. Yeah, you could say, well, yeah, that's fine. Yeah, it doesn't define a different way. I say it might build it up in a different way to get to the, but let's scratch that. So that's it. That's it. That's linear momentum. Now, I guess you could represent that as, in terms of the definition of fundamental theorem of calculus, that any derivative is defined as the limit as delta t goes to 0 of the change in momentum, linear momentum over the change in time. That, you can always take a derivative and think about that derivative is coming from. So the momentum is changing. And the reason I write it like that is because I just had a brain fart. I wanted to lead you to the criteria for conservation of linear momentum. It just oh yeah. Let's look at a problem we've analyzed so many times before. A block sitting on a table. What are the forces on that block?
Normal force, gravity.
Good, David. What is the net force on the block equal to? What value?
0.
Good. Is the momentum of the value, so since momentum is defined as mass times velocity, I should say that I didn't. So, and also it's a vector because velocity is a vector, and it gets its vector nature from the velocity because mass is not a vector, it's constant. And the units are just kilograms meters per second. So the units of momentum doesn't really have a name. Of linear momentum is kilograms meters per second. Okay. Now, back to this. Is the velocity of this thing changing?
No.
Yeah. So is the momentum changing?
No.
No. So you said the momentum is not changing, and you know that the net external force on the thing is what? Did you answer that already?
The net force is 0, yeah.
Is 0, yeah. So look what happens. Look what happens up here. If the net external force on the system is 0, then again, using either, I could use either one of these. And when I use this version, it just goes back to the first law. It's just a matter of perspective. So when the velocity is not changing, basically, we say that the acceleration is zero. And that just takes us back to using the first law. That's why I was asking, is the first law or the second law? But if we look at this version of Newton's second law from that point of view, then what we can say is, look what happens. Like this thing is zero here. So what we have is zero equals basically dp dt, but in terms of just basic principles, a change in momentum over a change in time. Now, you see this in math a lot. When you get a statement like that, a ratio or something like that, they might ask you, which one of, in order for this statement to be true, which one of these quantities, delta P or delta T, must be equal to zero? So David, answer.
That's a good question. I'm not too sure.
Do
Yeah, because
remember that question?
you could solve for either of them and they could be equal to zero, because you could divide the right side by delta P and divide the left side by delta P. And that'll be one over delta T equals zero. Or you could do the same with what's it called? Wait, no, hold on. Am I tripping right now? My bad.
Yeah, it's one of those trying to trick questions. It's not really a trick question, but it has implications. And you're not solving for anything. Like this is the value and it's equal to zero. So you don't have to solve for, I mean, I guess you could try to do that to see which one, yeah, if you want to solve, but it's not really, it's like the result of the thing. I don't know if, how could you?
It would be
'cause like,
delta P would be equal to zero, no?
why? Yes, that's true. It's
Because
why.
you can't divide by zero.
There you go. You can't divide by zero. That's one way to look at it from a mathematical point of view. But the other thing from a physical point of view is if you're observing a system, because what you're doing is observing the momentum of a system, right? This is the system. If you're observing the thing, you're doing that in time. So there's no way that delta t could be zero if you're observing it, because time has to pass for you to observe it, right?
Oh, so that, okay, I see that. So that makes sense in like a real world like situation, because time is always moving forward.
Yeah,
So it
yeah,
can never
like
be zero.
in the,
Well,
well, delta
yeah,
t can never be zero.
yeah, because it's starting at the very, very beginning, it'll be zero, but
Right. And again, this is kind of the way how I do it, because even with math stuff, I need to apply it to a physical situation or a possible physical situation, or some sort of applied situation. That helps me to understand it better. A mathematician might give the answer you gave, because that is a very strict answer. You can't divide by zero, and that's valid. That is true. So this thing must be delta p, and that's the answer that you get in math class. Because a lot of times when you have functions like that, they're not applied to. You're not doing it in the context of a physical situation. But I just think that that perspective helps even more. Because here's the other thing: even stuff in math that you don't know, because there's a whole, sometimes theory leads experiment and practical application or applied math, and sometimes practical things you figure them out, but you don't know how they work. So, experiment gets ahead of theory. So I guess I mentioned that because why did I mention that? My brain is fried too today. I don't know. I guess I was just trying to say that it's always good to kind of tie it to something practically. And for me, that helps me to understand it a bit better. I don't know, I lost my train of thought, so I don't know what I was trying to say. Point is, delta P is actually zero and delta T is not. So you can just say that in order for equation A to be true, delta P must be equal to zero. And just like that, you get conservation of momentum, conservation of linear momentum. This is a statement of conservation of linear momentum. And you can see it's similar to delta E equals zero, right? Be careful, this is a scalar equation. This is a vector equation because momentum is a vector because velocity. So what that means is that momentum final minus the momentum initial equals 0, another statement of the same thing, or that momentum final equals momentum initial. All three of these are valid statements of the conservation of linear momentum, but equation 11 is the most practical one. That's the place that we're going to start when we do problems, just like that's the place we start usually when we do conservation of energy. So now you have to backtrack. I'm going to give you a few minutes to think about it. This is conservation of linear momentum, and we developed it. We derived it. What had to be true in order for us to get to this? In other words, what was the criteria that happened somewhere along this derivation such that delta P was equal to 0, such that the linear momentum of the system is conserved? Because it's a general statement for any system in which this is true. Whatever the thing is I'm asking you, it's true for any system where the linear momentum of the system is true. So think about it for a second, too, and then tell me, or if you know the answer, tell me. You can go back and look through the steps of that derivation to see what it is. Anyone? Well, what was the first thing that I asked you?
It's because is it because it's not moving? The block?
It's related to that. Why is it not moving? And it's not
Because
so
it's
much
a
about
conservative force? Or sorry, force conservative what sorry, I'm what is it called? It's conservative.
you're overthinking. What two forces did you tell me were acting on the system?
Gravity and the normal force.
Is the normal force a conservative force?
No.
No. So the answer is no, then that's not the answer. But you're overthinking it. What is what is the motion of the it's not so much about motion, it's about acceleration. Because I could design a thought experiment where there is motion and still momentum would be conserved. In fact, I'll do that in a minute. Let's just stick with this for right now. It's not about the motion, it's about the acceleration.
It's not going anywhere.
Why?
I mean, it's not
Why?
accelerating.
It's not accelerating, but why isn't it accelerating?
Because there's no other force acting on it other than the normal force and gravity.
Well,
Or am I?
yeah, but that is a true statement. That's true.
It's true, but it's not right.
But like if you go to the problem up there, on the other problem on the board up there, let's say that I was sliding down a ramp and there was no friction. So if it slides down the ramp, the only two forces on are still normal force and gravity, but it would be accelerating.
Yeah, I see what
So
you're saying.
Yeah, even in this case, that's true. That's not the reason that it's not accelerating.
It's on a flat surface.
Yeah, that's related to it. And what about that? What does that mean about the? Let me ask you a different question. What is the net force on the system?
0.
And according to Newton's laws, what is the ultimate reason that you would have no acceleration on an object between the first and second law?
Would be inertia.
I mean, I need a complete statement.
Or an object in motion wants to stay in motion. And an object at rest wants to stay at rest.
That's not the full statement. You gotta say the whole thing. Right?
My bad. I'm really sleepy.
I mean, an object at rest doesn't necessarily want to stay at rest. You know, like that's not the full statement. That block on the plane is at rest, but if I turn it, you know, to if I turn the angle of the plane, it might want to stay at rest, but at some point it won't. Why? And the
So
same thing about moving down the road, right? Like at a constant speed. So what is the whole law? Don't just state part of it. You can't just state part of it. You can't just state part of the law. What is the whole first law? What is the whole first law? Well, good though that you made sure. Go ahead. But just if you have to look it up, look it up. But what's the whole thing?
an object in motion remains in motion unless it's acted on by another force
Well, not another force,
or another
but I can see how you can get that from the alliteration of the words. By the net external force, by a net external force.
okay.
Yeah, that has to be in there.
Okay.
An
and
object will remain at rest or in motion unless acted upon by an external, a net external force, which implies that if it's acted on by a net external force, what happens?
it'll begin accelerating.
Yes, yes, that's it. It will accelerate. So it's almost like when Newton wrote it, the implication of the second law is embedded inside the first law. Like you get directly to the second law by understanding the first law. So it's really those things you want to think about when you're thinking of now go back over to the momentum equation, the one where the second version of Newton's second law, net force equals change in momentum. So the net force becomes a little, it gives you a different perspective about what the net force is and what happens if it's not zero or if it is zero. You know, like it's just, that's why perspective is a theme of the course, because this is still the second law we're talking about, but we're looking at it from a different point of view. So whenever the net force is zero, the momentum will stay the same. Now, the example I gave you with the block on the table is a trivial example, but it's not about the motion, it's about the acceleration. So you know that if you put these two kind of forms together, forms of Newton's second law, and also keeping the first law in mind, when the net external force is zero, that means that the acceleration has to be zero and the velocity is not changing. And that is the only time that that's when the momentum is not going to be changing. It has nothing to do with whether the object is moving or not. It has everything to do with if the object is accelerating. If the object is not accelerating, the net force will be zero and the momentum will be constant for the system, no matter what is happening in between 2 points or 2 time periods. So what I'm trying to say is, can anyone, based on that, give me another example where there is motion, but the momentum will still be conserved? What is the obvious example of that scenario?
Would it? I don't want to sound ignorant, but
don't be afraid. Just, yeah,
all right. So if I'm in a car going at a constant, like if I'm just going 60 miles an hour and I'm not like speeding up or slowing down, would that be an example of that?
And you got to kick. Yes, it would. Very good. And you're not, but you also have to throw in direction, because
Oh yeah,
speed is
sorry, yeah, straight,
straight line.
like
Yeah,
straight line, yeah.
awesome. Yeah, so yeah, you got to take a chance in order to get the reward, right? Yeah. So that's exactly the situation. Anytime an object has a constant velocity, you know, it also is, its momentum is conserved. That's very important situation to keep in mind. Yeah. Yeah. So good, awesome, awesome. So that's in the simplest case, that's it. That's just that's the conservation of linear momentum, and we can use it to solve problems and do collision problems and things like that. I'm probably going to do something before we go there. I'm going to talk about impulse because impulse has to do with, so momentum is conserved when the net external force is zero, but sometimes momentum changes, so it's not always conserved. So we can deal with that, and that's still, we would still use the second law to analyze that situation. because using that second form of the second law. It's only when the net force is equal to 0 that the moment delta P is 0. But when the net force is not equal to 0, then delta P, then the net force is equal to delta P over delta T. And that gives gives different kinds of problems that we can look at. So let's look at those right now before we go into using conservation of linear momentum to solve collision problems. So this is not necessarily, so when the momentum is not conserved, then you have a net force on the object. And so let's talk about what that looks like and how we can use that to apply to certain types of problems. Time is it? Oh man, we only got 20 minutes left. Class went by fast. Why is that? Oh, because I spent the whole first hour doing center math. Forgot about that. Man, I'm tired. I think I need to take a nap after this. But let's do it. So this is a criteria. So what happens when the net force is not 0 and we're looking at it from this point of view? So this gives rise to a class of problems called impulse problems. Impulse. What is the term impulse? When you use that term in everyday language, what does it imply?
You just do it without much thought. It's an impulse, or it just
Yeah.
happens, sort of.
Yeah, it just happens without much thought. That's in terms of thought. When you apply that same concept, impulse, to time, that not much thought means that because it takes time to think, right? So impulse, if you're not doing it with thought, in terms of the amount of response time it takes you to make a decision and do something on impulse, as opposed to when you're doing it by thinking through it, what is the difference in those time periods, you would say?
Well, then I'd say like when you, okay, so then I make the distinction by saying when I do something on impulse, I do so in 0 time, I guess you could say. Like it's just
There you go.
0 time.
0 time, or a very, very short amount of time compared to when you're more contemplative about something. Yeah. And so, so it's the same in physics. Impulse problems are problems that occur when you have a change in acceleration over a very short amount, extremely short amount of time. So there would be problems like, hitting a ball with a bat, right? The ball changes its direction extremely fast, or a basketball bounce, any kind of ball problems, right? Ball problems, tennis ball, golf ball, throwing a ball on a wall, even a punch, like a boxer punching. In fact, when you're punching, you're supposed to you go look at those pictures of Muhammad Ali, dance around and jab, and it's not that he just like for the same force, if you punch like that, right, like you hit and hold your hand out, which one do you think you'll apply the more force? Doing that or doing this? And why?
Wait, sorry.
So this is one punch. I'm gonna just punch and hold my hand out like that.
Okay.
Now let's assume that I'm throwing the punch with the same force, the same amount of force, right?
Yeah.
But I throw the punch like this, and just imagine it's landing on the person, right? It's going to take a certain amount of time to slow down. I accelerate my fist to some maximum velocity, right? But then when it hits the person, it has to slow down over a short amount of time. Fine, okay, so it does that. If I punch it straight out and hold my hand out like that, then that would apply a certain amount of, well, it's not so, it's the same force, but impulse we'll see as a different physical concept than force, but it's related to force. But just think, I should ask the question differently. What do you think would do more damage? A punch like this, where I punch and I hold my hand, like just hold it there and, like on the person's body or face or whatever, or a punch like this?
The second
Which
one, the
one?
one you just did.
Why?
because you came back immediately.
Yeah, and in fact, when you see the best boxers and the people like Muhammad Ali were the best at this, when you see him like shadow boxing, if you take a look at his, like it's almost like the hands, the wrists are like, it's kind of like it's like the best boxers. It's kind of like with jabbing, not with punching. It's almost like the arm and the hand are two different things. So that when you jab, you're flicking your wrist, right? And when you flick it, it makes it quicker. It makes it apply the force quicker than certainly holding a jab like that, or or just punching straight through. Now, a knockout punch, you want to punch straight through, but jabs actually, that was one of the things that was really significant about Muhammad Ali being a heavyweight fighter, because he was probably the first person that was a big dude, like over 200 pounds, that danced kind of like a middleweight, like that dance and box like a middleweight, because he was so quick, but he was huge. He is big, right? Big dude. And you didn't, before that, heavyweight boxers didn't box like that. Maybe Joe Louis was the closest thing, but most of them, they were just big, and they could be quick and strong and fast, but fast is different than being quick. A lot of them were fast. Much of them were not quick. I mean, Muhammad Ali was quick as any of these smaller boxers, like any of these like welterweight, or he was that quick, but he was a big dude. So, he was knocking people out with jabs. Like it didn't look like he was and he wasn't that much of a he wasn't that as powerful. You can look at a fight like another good fight to look at would be between him and Joe Foreman, right? Joe Foreman was a big dude. He was like, oh my God, that dude was so big and strong and hard hitting. But look at the fight where he beat him the second time, or I guess it was the second time, or maybe the first. I don't remember. But the one where the Thriller in Manila, and George Foreman's got him on the rope and just beating the crap out of him, like, and he's doing that rope with him hanging back, and then he jumps out when Foreman gets tired, and then the punches are so fast, and he's flicking his wrist and it stings him. Because he connects and Foreman goes down, and he just needs 10 seconds. That's one good fight. Another good fight is the first time he became a champion when he was really young, and he beat Sonny Liston. And I think it was I don't remember whether it's the first Sonny Liston fight or the second Sonny Liston fight. People thought that Sonny Liston, well, I think he did kind of throw the fight the second time around, but the first time, Ali knocked him out, and you almost don't even see the punch. And the punches aren't that hard, but they're fast, and he's very accurate. So he's putting the punch right on the head, right, like right on the jaw. So that quick punch, it snaps the head, and what knocks you out is it causes your brain to kind of jiggle against your skull, and then it causes, like, I don't know what physiologically happens with oxygen and stuff, but when that snaps your head like that, your brain hits against your skull, and it causes you to faint. That's what a knockout is. And Ali was just a master at it, That's why he didn't really go to the body much. He knocked people out by hitting them very quickly, in the face before they could see it. And that's what what I'm saying here, this is the physics of what was happening there. Like, you throw the punch and you flick the fist, and it hits a person, and it delivers a very high impulse for an average. So given the same amount of force, the quicker you deliver the blow, the higher the impulse. And that makes a big difference on how you're changing the momentum of the thing that you're hitting. And so we'll see that right now. So we get it directly from Newton's second law, that net force from this version of Newton's second law, that net force equals change in momentum divided by change in time. Now I'm going to take the delta T over. And what we get is that delta P then is equal to the net external force applied to something times the time in which that force is applied.
Now, for the same amount of force, well, you can see it here, but definitely for the same amount of force, the smaller the delta t, well, you can really see it here. I guess I should say this, that the change for the same change in momentum, which would happen, yeah, this is a better way to see it. For the same change in momentum, and what is change in momentum? It's mass times velocity. So the person, like, I think boxing is a good example of this. You only have so much mass. Your arm is not going to change its mass, because that's really, and there's some momentum here that you're getting with your body, but really it's the mass of the arm that's delivering the punch. Now, you can't change the mass of your arm, but you can change how fast you're changing the momentum.
So that's why so I don't mean to cut you off.
Go ahead, that's all right.
I was going to say that's why the flicking at the end is very important, because the less time that is, the smaller t is, delta t is it increases force.
Exactly, because you already got two things going. That's why I was saying it's the difference between the arm and the wrist. Your arm, you're trying to throw your arm out and bring it back fast, right? And the momentum of your body, it's almost like when you see boxers, the best spotter, it's like this whipping action that starts at their feet, right? You know, you can, like, it's like you're whipping you're kind of throwing your body and then whipping your arm so that you can, you start off with a large, acceleration of the arm, but then you want to kind of pull your body back so it'll help you. You're using the momentum of your body to also pull your arm back, and you practice doing that really fast. That's what Muhammad Ali was excellent. And that whole stuff about the, when he would get out there and shuffle his feet and stuff like that, he would kind of play it up, right? Like it would scare people, which it probably did, and it also distracts people when you're doing that, because a lot of boxers didn't do that. He would do that, right? But you notice he always did it right before he was about to deliver a series of punches. But what that actually does is it shifts the momentum of your body. And first of all, it confuses him, because you don't know which punch he's going to come with, the right or the left, when you start doing that, because he's doing it so fast with his feet. But it's also shifting the momentum of your body, so that very quickly you'll be able to kind of, it's almost like you start the punch while you're doing that pedaling, but then you stop right in the middle of the punch, and it helps you to pull your arm back, and it also contributes to the whipping motion of your body, and it causes that if your hand is loose on your arm, it causes it to whip, and all of that whole process is a very complex process actually. All of that causes the amount of time that the fist is in contact with the body or the face to be smaller. And he was just, I don't know if you can teach people to do that. I think you can, but he was just one of those people who was just talented like that. You can see boxers, some boxers kind of, they're big, and some boxers are a little bit more boxy, I don't know. And he, like I said, he was a heavyweight who just had that kind of rhythm, and it's talent. That's what, when you talk about talent as a boxer, that's one way you could measure talent. It's people who are naturally able to do that. And it just all of the whole ultimate purpose is so that you can deliver a punch quicker and cleaner. And if all that stuff is distracting people and they don't know what to do, it kind of confuses them for a split second. And it also allows you to be more accurate, because they're trying to busy think about what's coming, and so they're not really moving around. Like, it just happens very fast. All of that kind of works together if you know what you're doing and you know how to do it. But the basic physics is really, that's that shifting back and forth, is kind of shifting the momentum of your body so that you're able to deliver a quicker punch by kind of maneuvering or manipulating the momentum of your body relative to your arm, and how that affects the punch. So none of that stuff, like, he kind of played it up and was making fun, like, but all that stuff is straight up physics. And it's why those punches were so effective, and the way that he fought. So yeah, that whipping motion, it decreases delta T, and for the same amount, because you can only be so strong and so fast. So that's why throwing a punch like that, and I'm just very crude at it, right? Because there's other stuff that I could do to make it even quicker. But throwing a punch like that, as opposed to throwing a punch like that, is the second punch, the same change in momentum. Well, actually, it's not really the same change in momentum, because throwing it out, like, we'll see that momentum is a vector. That's another thing, that even if I weren't very quick doing this, that the momentum goes from 0 to from maximum momentum to 0. But then if I then bring it back, it goes from 0 to a maximum. And what we have to realize is that in this top quantity here, the delta quantity is always final minus initial, but it's a vector quantity, unlike energy. So the delta P is like the final momentum minus the initial momentum, but then they're in different directions. So if you establish this as the positive direction, I throw the positive momentum, that's initial, but then I'm coming back in the opposite direction. So that's a minus sign associated with the quantity. So you get a minus and a minus, and you get a plus. So the change in momentum is actually going to be 2p, not 0, obviously, because if it was 0, you would get 0 force, right? Because this can't be 0, delta t, like we just said. So for some, if I'm throwing, so the very minimum, like if I pull my hand back at the same time with the same change in momentum as I deliver it, at the very least, the momentum would be 2p, right? But depending on how fast I do that, and they don't actually have to be equal, but you get a larger momentum because of the time in which you deliver that change, that full change. So, yeah. Now in the as delta t goes to 0, then this really becomes a derivative. That the delta p, the change in momentum, is really equal to the summation becomes an integral. So it's integral over the average force times delta t, times dt. Now, the reason that we actually have to acknowledge it in this way is the following. Let's think about like a ball hitting a wall. I think I might have to go here. 5 minutes. Yeah, I'll finish it, and then you can want to read through the chapters on this. We really have to deal with average force here, not actual force, and this is why. Think about what happens when a ball hits a wall. I don't have a ball here with me, but just let me just dramatize it here. There's always going to be some sort of deformation, even with the fist, right? Like with the punching thing, the glove is spongy, but it kind of deforms in a certain way. But let's think of a ball. Let's say this is a round ball right here, and I throw it against the wall, and my hand here is the wall. If you actually had a time-lapse camera and you could look at what's happening when the collision occurs, this is what happens. It's something like this. The ball is going, it's at a certain momentum. It starts to hit the wall. As it slows, it doesn't just stop instantaneously. It slows down and compresses. It deforms and compresses, then stops, and then rebounds off of the wall as it regains its position back, and then moves in the opposite direction. Okay, so now think of the third law, because when the ball is applying a force to the wall, the wall is applying a force to the ball. That's what's made it's the reaction force that's making the ball deform, right? And so if you can imagine that the ball is deforming, like right as soon as the ball hits the wall, there's a certain value of force, right? It's 0, but then it starts at 0. Then what do you think happens to the reaction force as the ball is compressed toward the wall? Does it increase, decrease, stay the same as through this entire process? And then as it backs off the wall, if you could plot force per unit time, so on the y direction, this is force, and assuming that just as the ball makes contact, we're starting at a force on the ball of 0. What do you think the shape of the force curve would look like? Just draw it on your piece of paper right now. And let's say that right here in the middle is where the ball is fully deformed. and let's say that, yeah, fully deformed. And then just draw what the curve is you think would be, what it would look like. And obviously, let's say that this time period over here, so this is T, but let's say that this time here, say T is a T final or something like that, where where the ball that then comes off the wall. So T initial is at T equals 0, where the ball hits the wall. Halfway in between is where it's fully, the ball will be fully deformed. So maybe you could say that in an ideal case, I guess that would be 1/2 TF. And then this is TF, where the ball leaves the wall in the other direction. So graph a curve of what you think the reaction force, the Newton's third law force of the wall on the ball looks like.
Would it look like a bell curve? So it would start at the origin and then be at the max at the fully deformed.
Awesome, dude. Who is that? Is that David?
Yeah, I woke up.
Dude, you're on the ball this morning or this afternoon. Yeah, you get a Gaussian. Loosely, we call it bell-shaped curve. That's what you call it, but it's actually, the official name is a Gaussian distribution. And a lot of things follow Gaussian distributions, like grades and all kinds of stuff. Well, we won't talk about that. That's in terms of the mathematics of it. But the reason that I mentioned it is that that's not a constant curve. That's not constant, which means that the acceleration of the ball as it is being in impact is not constant. At the beginning of the course, I told you mostly we deal with constant acceleration. And so we can actually, and we've done several problems now where we've explicitly figured out the equation of motion because we knew the functional form of the force. Either it's constant mg, or it was, like a Hooke's law, it was depending on coordinate, it's kx, or drag force, it was dv or dv squared. All those problems, we actually knew what the force was, the functional form, and so we could derive the explicit equation of motion. The thing about a Gaussian curve is that it's very difficult to get. It's like an average value of all the things, the forces that are contributing to the motion. And they just kind of, I don't know why this shape, well, I do have a reason why the shape is like that, but it's complicated, really complicated. And if you think about a ball, so to actually get the functional form of what that curve would be so that you could explicitly graph it. And you need to know that if you want to know an explicit equation of motion, because F equals ma, right? You got to start with that. And just think about like when you think about a ball, there's so many factors that are, like if it's a rubber ball, so many factors contributing to how it bounces off the wall. Things that are not even associated necessarily with what, if you want to consider the ball, the closed system, the ball in the wall, you really can't, because there's other things like the temperature in the room that are affecting, how the ball is reacting to the wall. And all those things, you would have to know in order to explicitly know the functional form of the reaction force, because that's also contributing to the force of the ball on the wall, and they're equal and opposite. So it's contributing to the force of the wall on the ball. So in order to be explicit, you would have to know all of that. The humidity, the temperature in the room, probably the density of the material. I don't know. So usually when we get Gaussians, we figure out other ways of dealing with it, as opposed to knowing the explicit function of the force. And in this case, we do. We can know that over time, if you look at a lot of experiments, there's a way of calculating the average value of the force. And it would look something like this, because we know that basically, if we can get an average value of the force, which is for a Gaussian is something like this, then we know that the area under a curve of, like if you, when we look at it like this, when if we wanted to calculate the area of this curve, we would multiply F times T. But we have to see when we look at this equation that F times T is actually units of momentum. So when we plot an F versus T curve, what we can see is that it's approximately equal, the area under the Gaussian is approximately equal to the area under the average value of the force. And that's very easy to to calculate. We can give that explicitly, even though it's not the explicit force, it's just the average value of the Gaussian. And therefore, we can deal with the average force as opposed to the actual force in determining the area under the curve, which is the impulse, in order to work the problem. And so this is one of the third times you see, and maybe second or third time you see area under the curve being something. The area under the F versus T curve is the impulse or change in impulse of the problem. So first time it was area under the velocity versus time curve was displacement. The area under the force times position was equal to the work done. And now the area under the force times time curve is equal to the impulse. Yeah, so then we just define that as impulse. And impulse then is defined as the change in momentum. So we get two equations out of that. That impulse is equal to change in momentum, and it's defined that way, but also it's equal to the integral of F dot, it's not a, of the average force dotted into dt. It's not a dot because time is not a vector. Well, actually, yeah, I guess really you get three equations. That delta P is equal to that, but because impulse is defined as delta P, then you can also say that impulse is equal to the integral of F average dt. And you get a graph because you can use a graphical representation to solve problems as well. So that's what impulse is. And we apply it to any problem where there's a couple criteria. One is where it happens over a very small amount of time, but what does that mean? You know, it's all relative, right? Time anyway. So really what I like to say is kind of the small time in conjunction with the fact that you get something like a Gaussian distribution that would describe the force of interaction of the object or the system in question. So it's not just short time, but short time and such that the acceleration is changing over that short period of time in such a way that it's not constant. And so that's always going to be any kind of problems like balls hitting something, ball hitting a wall, a boxer hitting a bag, you know, a baseball, you know, player hitting a ball, a golf ball, anything like that, or even bumper cars colliding. It's another situation where the collision is like milliseconds or, you know, something like that. And so you always are going to have a scenario like this where you wouldn't really be able to calculate the exact force in a way that's practical. So we can use these and we'll show you how that actually gives, you know, exact, very accurate parameters for finding the velocity and everything. Because, you know, like remember, momentum is changing velocity. So mass, change in mass is momentum is mass times velocity. So we can use that to solve for kinematic quantities like velocity of a changing system. Yeah. So, well, that's the introduction. Where I guess we're out of time now, but we'll work some problems with this kind of thing, and also get into collision problems and use both conservation and energy and momentum to talk about what we mean by collision problems and how to work through those with some efficiency and know-how. All right, so I guess that's it. If there are any other questions, I guess we're class dismissed. Yeah. Anything? Questions?
I think yeah, I have a question. So
Yeah.
I understand that when the ball this is going back to the example of a ball being thrown at a wall.
Yeah.
So the ball expanding back to its normal shape, I guess I'll call it expanding. Does that play a part in its force as it leaves the wall, if that makes sense? Because or is that just something that happens because it's, I don't know if I'm wording my question correctly, but like if like my fist is right up against the wall and then I expand my hand will move back a little bit because I'm like expanding it to the tips of my fingers. Mm-hmm. That's like I'm causing my hand to move backward because of its own, because I'm making it do that, the force from my fingers. So the ball expanding, is that like a force that's making the ball go back as well?
Yeah.
Oh, okay.
Yeah. So like, look here. This is the first half of the trip. That's why I broke it into two. So as the ball hits the wall, it starts to deform and flatten out, right? So what do you think is happening to the force that the ball is applying to the wall as that happens? Is it getting greater or smaller?
Greater.
Greater. And that's just like compression, right? Like if if someone is squeezing you, you can feel more force as your body is compressed. Well, that's what's happening when you run into a wall, right? Like
Yeah.
it's like it's just more pressure on your body. And so the reason this thing is compressing is because and I know we haven't defined pressure yet, but the pressure actually is increasing, and that's what's causing the ball to deform. But it's increasing because as more surface area is in contact with the wall, there is more, well, actually pressure is equal to force divided by area. So the area is increasing. So area times force is equal to, so area times pressure is equal to force. So for the same amount of pressure, if the area increases, the force is going to increase. So basically you could say that as the ball is, the thing that's making the ball compress is that the force is kind of increasing. That's why you get a Gaussian like that. And then, sure, like right now, at that point, I guess the ball, it has to respond or rebound. It's rebounding because now it's expanding on its own. It's doing exactly what you just said. Like it's basically pushing off the wall, essentially. But as it opens up, the force is not constant because the farther it's, the more it kind of expands from being compressed, the less it's in contact with the wall. So the force is going down again.
Right.
And then it leaves completely, the force only goes to zero when the ball is not in contact with the wall at all. Now, what this Gaussian implies is that for a ball, it's happening symmetrically. That's not necessarily the case. It might, you might see some things, like in reality, sometimes maybe you might see something like that, where it's kind of swayed on one end, usually probably more like this than the other way around. But I'm just dealing an ideal case. In an ideal case, you'll get as much compression, as much average force above as below, and you might get a very smooth Gaussian like that. Like if you did your hand on the wall like that, it might be all mucked up. I mean, who knows what it might be something, I don't know, like, because, it's not like a ball where maybe it wouldn't be that bad, but maybe something like that. I don't know. Because your hand is not like a uniform ball the molecules are being compressed and then expanding in the same way, because you have muscles in your hand, and like it's not gonna, even with a punch, I don't think if you had a punch wouldn't be that smooth. Like even for someone like a professional boxer, there might be some variations in it because it's not a ball that is uniform and all that. But if you had a uniform ideal ball, you would have as much compression before as after. And so the average force would go in on itself and then back out in the same way. And so you might get a very smooth, nice Gaussian like that. But what you can think of is that in the beginning, there's compression, and then in the second half, there's expansion. So I think your thinking is right in that way.
All right. Yeah, I understand.
Now, when we take the average value, we're not considering that. We're assuming that the average value, because see, this is not a changing force. It's assumed that the force is constant. So it's an approximation. But it's an approximation that pretty much gives us the same answer for some reason. I don't know, it just works out that way, which is why we use it. So, because it would be a lot more difficult to do this problem if we were doing it in the way that we've been doing problems in the previous chapters. We would have to actually get this force and then integrate it and then use that to find the acceleration. It's a lot of work, particularly for something that's really complicated. So what we do is this kind of process instead, and we're basically just approximating. But the approximation is very, very, very close to the original. And the graphical illustration here shows that it generally is. But this is implying that the force, once it hits the ball, once the ball hits the wall, it's not changing at all, which doesn't really make sense because we know that on some level, there's always compression. Now, maybe you have a really hard ball, so there's not a lot of compression. That might be a situation where this is more true. But even in that case, it would be more a situation, I would think, where the Gaussian would be, I don't know, it would be something kind of like for a really hard ball that doesn't compress that much. It might really be something more like that. I don't know. It's hard to imagine, right? Where it's kind of flattened out more or something. Where then if you did the approximation, it's almost like the average value is going to be very close to the thing, like if it's flattened out like that. I don't know, maybe not. It's probably still not working very well. I guess it doesn't, if that makes sense or not. I don't think it does. But yeah, I don't know. I don't know what I don't know if there's a way to, yeah, I don't think yeah. So even in that case, even though it's not compressing, maybe on whatever level the compression is, I think you would still have a discrepancy between the actual changing force and the average value of the force. Yeah, now that I think about it. Yeah. Anyway, I hope that answered your question. That was a lot, but I hope I answered somewhere in there the question that you were asking.
No, yeah.